Hello, so today we are going to do this problem, which is part of Leetcode daily challenge, maximum nesting depth of the parentheses. So basically we have a concept of valid parentheses string. We call it VPS if it meets one of the two criteria we have here. If it's an empty string or just a single character without any parentheses, then we say it's 0. The depth is 0, but it's a valid VPS. Or if it can be written as AB, where basically it's a concatenation of two expressions of two VPS, then it is a VPS. So you can think of that example is like with something like 1 like this. This is a VPS, right? And this one is A, this one is B, okay? And then if you look at, so these are the two examples. The other example is A is a VPS, and then you have a parenthesis in between, right? So that can be, for example, like this. Since this is just one character, this is a VPS, or it can be something like this, a parenthesis, another one, and then you have 2, and then you have another one. So this is a VPS, and then you have the parentheses. And then we are defining also the depth of a VPS as basically the number of parentheses a character is inside. So for example, the depth of just empty string is nothing, there is no parentheses. For C is 0 if it's just like the character, let's say like 1. For A plus B, it's the maximum depth between the two, if you have two concatenation. If you have A and then A itself is between parentheses, then the parentheses count as 1, and then however the number of the depth of A is, and so 1 plus depth A. And the goal of the problem is to return the nesting depth of S, okay? And so basically you can think of it as how many parentheses each character is inside of, we return the max, right? And the length is not too long, 100, so we should be able to do an O(n) solution fine. Now, how do we tackle this? Well, with parentheses in general, especially open and closed ones, usually what you have two ways to do it. Stack, you can use a stack, or you could use like keep track of a balance, where you increment the balance on an open parenthesis, and then you decrement it on a closed parenthesis, okay? So if you have another, so this is an open one, you increment the balance, and then if it is closed, you decrement the balance. We'll start off with the stack approach and then do the balance approach. But usually if you have parentheses, you are asked to validate it or count the number of parentheses or something like that. Those are the first one to think about and try. So if we try a stack, if you look carefully here, for example, this one, what is the max depth? Well, the max depth, this one has a depth of 1, this one has a depth of 2, this one has a depth of 3, so the maximum is 3. Now, how do we count the depth? Well, if you think about it here, it actually suffices to just count the number of open parentheses before a parenthesis gets closed, right? Because let's say if this one gets closed, maybe there is another something like this, then we don't need to count this anymore for 3 because it was closed, so we only care about open parentheses. So that's why what we can do here in the stack is just add the open parentheses and remove it when we encounter a closed parentheses, right? And so let's do it for this one. Let's remove this. So first we add open parentheses, and then when we encounter one, we don't do anything. When we get a closed parentheses here, at this place here, we remove the open parentheses, okay? But every time we want to see how many open parentheses we have in the stack so we can get the max. So let's keep track of the maximum, let's call it maximum depth. And each time we can just say the maximum, it's going to be just the maximum of what we have, and the length of the stack, because that's how many open parentheses we have, and that's exactly what would be the current depth of the stack. And so with that means right now we have max depth depth is equal to 1. So when we encounter closed, we remove it, and then we get an open one. It's still, the length is 1, so this stays the same. When we move here, we add another one, right, for the open parentheses. So now we have 2. The length of the stack is 2. So we update. Close, we remove. Close again, we remove. And then we get an open. We get another open. And so I think there is a third one. Yeah, there is a third one like this. And then we have a third one. We update the depth, now it's 3. And then we close, we remove all these 3. Okay, and so the maximum depth is 3, right? So that's the simplest approach we can take here. So we can have a stack, and we can go through the characters in S. And we can just check if C is equal to an open one, then we add it to a stack. If it's equal to closed, we pop from the stack. Okay. If it's neither of these two, we don't need to worry about it. But also here we need to update how many open parentheses we have in the stack. So we need to use this. And we need to define our max depth as 0. Then at the end, that's what we return. And we can submit. And this works, okay? Now, in terms of time complexity, this is O(n) time, and then we are using this stack for O(n) space. Now, with the balance approach, we can actually get this down to O(1) space because we only need to keep track of how many open ones. If you think about the stack, what the stack is doing is just keeping track of open parentheses, and once we close a parenthesis, it just removes it. So we can use the same thing for the balance. We can actually call it even current open parentheses, for example. Okay, so we can call it like that. Start with 0. When we encounter open, we increment it by 1. When we encounter close, we just decrement it by 1. And then here we are only interested in open parentheses, and that's pretty much it. So we almost do the same thing, but with just one variable. And so if we submit, that gets accepted, and this is O(n) time and O(1) space because we are only using one extra variable. Yeah, so that's pretty much it for this problem. Thanks for watching, and see you on the next one. Bye.